This course covers the MIPS32 architecture virtualization module for MIPS processors. This section describes the virtualization module as it pertains to a MIPS core implementation. First, I'll explain what virtualization is. Operating modes will cover the new modes added for assisted virtualization. The virtual memory section covers the use of the TLBs to control memory access. Exceptions covers exceptions within the context of virtualization. Interrupts covers interrupts within the context of virtualization. The hypervisor resource section covers how core resources are configured and protected. In the multi-core section, I'll discuss how virtualization pertains to a multi-core system. In the multi-threaded section, I'll discuss how virtualization pertains to a multi-threaded core and a multi-threaded multi-core. The System Control CP0 register section covers CP0 registers that are related to virtualization. Simply put, computer virtualization makes one physical computer look like any number of physical computers. It allows the running of multiple operating systems, multiple embedded programs, or a combination of both. It does this by separating the software running in these virtual machines, or VMs, from the underlying hardware resources. Here are some terms I will be using. A host processor is connected to the actual physical hardware. A processor is synonymous with a virtual processor or VPE in a core that supports the multi-threaded ASE. A virtual machine or VM is a virtual context of the processor created by software. The root context is the context of the physical system. The guest context is the context of a virtual machine. There can be several virtual machines, each running a different guest OS in their own context. The software that creates and controls the VM is called a hypervisor. The hypervisor runs in the root context. It has direct control of the hardware and thus creates and maintains the trusted execution environment. The hypervisor is responsible for loading and controlling the software running in a guest context. The software running in the guest context will not be able to tell it's not running on actual hardware, but all hardware interfacing that this software does can be controlled by the hypervisor running on the host machine. Taking a small step back, the idea for computer virtualization is not new. In 1974, Gerald Popek and Robert Goldberg wrote an article called Formal Requirements for Virtualizable Third-Generation Architectures. In it, they laid out three main requirements for virtualization. Equivalence, where running on a virtual machine should look identical to running on the actual hardware. Resource control, where a hypervisor must be in control of the virtualized resources. And last, most of the instructions executed should not require hypervisor intervention. There are two types of hypervisors. A Type 1 or native hypervisor runs directly on the hardware or processor, and the guest software, such as an OS, runs in the VMs on the level above. Microsoft Hyper-V is an example of this type. A Type 2 or hosted hypervisor runs within a conventional operating system environment. These are also referred to as trap and emulate because all actions by a guest OS that need to affect the actual physical resources are trapped and the access is emulated. A common example of this is VMware Workstation that runs in the Microsoft Windows environment. On a standard MIPS core, the Type 2 hypervisor would run in kernel mode and the guest OSs would run in user mode. In this way, any access that the guest OS tries to make to a privileged region of memory or execute a privileged instruction will cause an exception that is handled by the hypervisor running in kernel mode. Fundamental to the virtualization module is the addition of a limited privilege guest operating mode. The virtualization module keeps the existing privilege mode and calls it root mode. For this mode, the classic kernel, user, and supervisor operating modes will be referred to as root kernel, root user, and root supervisor, respectively. Note, the diagram does not include supervisor mode because it is seldom used. The virtualization module adds a guest mode, which consists of a new operating modes guest kernel, guest user, and guest supervisor. These are orthogonal to the existing kernel, user, and supervisor modes. The virtualization module can selectively allow the guest kernel mode to handle some interrupts, guest exceptions, and manage virtual memory for the guest user mode process. The hypervisor handles all exceptions that happen in the root context and can selectively handle exceptions that happen in the guest context. 3 operating modes are required to execute a virtualized guest operating system: unprivileged guest user, limited privilege guest kernel, and full privilege root kernel. In addition, a root user mode can be used to execute non-virtualized software that needs to be secure. Root and guest mode each have their own contexts. The term context refers to the software visible state held within each coprocessor 0 register set. The virtualization module physically replicates a set of the coprocessor 0 register set for use by the guest operating system. There is only one set of guest CP0 registers per processor. The root kernel uses the full standard set of CP0 registers and additional CP0 registers used to control guest mode operation. During guest mode execution, both the guest coprocessor 0 and the root coprocessor 0 contexts are active. The presence of 2 simultaneously active coprocessor contexts is fundamental to the operation of the virtualization module. Exceptions can be handled in the mode whose context triggered the exception. An exception triggered by the guest CP0 context can be handled in the guest mode, and an exception triggered by the root CP0 context can be handled in root mode. For example, a timer interrupt that is caused by the root CP0 count register reaching the root compare register will be handled in root mode. A timer interrupt that is caused by the guest count register reaching the guest compare register will be handled in guest mode. For a simple switch between guest mode and root mode, the presence of 2 coprocessor 0 contexts and a shadow register set allows for the immediate switch between guest and root modes without requiring context switch to or from memory. Simultaneously active CP0 contexts for the guest and root allow the guest kernel privilege code to execute with a minimum hypervisor intervention and ensure that key root mode machine systems such as timekeeping, address translation, and external interrupt handling continue to operate without major changes during the guest execution. For a hypervisor to switch from one guest to another, it must save the context of the guest OS by switching out and restoring the context of the guest OS being switched in. The hypervisor must save and restore software visible state and the physical resources which are shared between guests, such as the guest CP0 registers, the root CP0 guest registers, the guest general purpose registers, the floating point registers, the high-low accumulator registers, and the TLB state. Some of the MIPS cores may require less register savings. For example, MT cores and cores with shadow register set can avoid the saving of GPRs. Cores with multiple FPU contexts can avoid saving FPU registers. The virtualization module can also be configured to avoid saving of the TLB state. The MIPS virtualization module allows the hypervisor to modify guest configuration by writing the guest configuration registers. In this manner, such a virtualization system can support privileged software from different hardware platforms by running them as guests with different configurations. This allows a virtualized guest to have features and capabilities which are a subset of the root host machine and different from other guests. For example, if the host machine has an FPU, the hypervisor can program the guest config FP field to not have an FPU. The virtualization module provides root mode software with controls over the privileged instructions that can be executed, the CP0 context registers which can be accessed, and the interrupts and exceptions which can be taken when in guest mode. There will be more on this in upcoming sections. Guest mode is controlled by the CP0 root guest control 0 MG bit. It is used along with the root mode exception and error status bits EXL and ERL and the debug mode bit DM to determine whether the processor is operating in guest or root mode. The processor is in guest mode when the GM bit is set and the root status EXL and ERL and DM bits are cleared. The virtualization module extension contains a hierarchy of memory management units which are used for the isolation of applications, operating systems, and the hypervisor. Specifically, a guest MMU is managed by the guest OS to isolate the guest application, while the root MMU is managed by the hypervisor to isolate the guest OSs and itself. Only the hypervisor is allowed to interact with secure code that controls the root MMU. That does the actual translation to a physical address. A hypervisor divides the actual physical memory up so that each guest has its own non-shared physical memory, and there is no overlap with the memory that the hypervisor uses. All guest addresses are controlled through the root MMU, even those that the guest OS sees as being direct mapped. A program executing in guest user space works the same as a user space program in classic MIPS. It always uses the virtual address that are mapped either directly using an FMT MMU or mapped through a TLB MMU. The guest OS translates the virtual address to a guest physical address. In the virtualization module, the guest physical address is a virtual address in the root mode context that the root TLB will further translate to a physical address. Guest direct map segments such as KSEG 0 or KSEG 1 also map to a guest physical address, which will further be translated by the root MMU. Lightweight virtualization supports a core with an FMT type MMU. This configuration provides memory protection without the need to manage TLB translations by the hypervisor. This is done through the Root Protection Unit or RPU. The RPU is a defeatured root TLB that checks the guest physical address on a page basis for execute inhibit, read inhibit, and dirty page attributes. Note the dirty page attribute write inhibits the page. It does not support address translation or the cache coherency attribute. The guest FMT translation produces the direct map physical address. If the action being attempted is allowed by the guest attributes, then the guest has access to the related L1, L2, and physical memory. Otherwise, the access will trap into the hypervisor using standard TLB exceptions. The RPU is programmed just like a TLB. However, the root entry low 0 and entry low 1 PFM and CCA fields are assumed to be read-only as 0. This table shows you the exception that is generated on failure if the RPU is being used. Bad vAddr contains the physical address of the source of the exception. Lightweight virtualization is intended to support a single guest. With it, you can protect the hypervisor code and data from any kind of access from the guest mode. If there are proprietary libraries that need to be protected from examination, they can be set to read inhibit, so only instruction fetches can be done. Both the hypervisor and the proprietary libraries can be write protected by setting the dirty attribute. A TLB type of MMU is used to support full virtualization features. There are two ways to associate TLB entries with a specific context of a guest software. A guest ID can be used to tag all entries in the TLB entry associated with a specific guest. The guest entry number is used when writing the TLB entry. It comes from the current value of the root guest control 1 ID field. The guest ID is active if the CP0 register guest control 0 RAD field is 0. The guest ID is used for both the guest TLB entries and the root TLB entries. The benefit of using a guest ID is that the guest TLB does not need to be flushed when the hypervisor swaps one guest software context for another. Instead of using a guest ID, the root address space identifier ASID can be used for the root TLB entries to associate with a specific guest with a TLB entry in the root TLB. In this case, all entries in the guest TLB will assume to belong to only one guest context. The ASID used when writing a TLB entry comes from the CP0 entry high ASID field. If the ASID is used, the hypervisor will need to invalidate the entire guest TLB when it swaps one guest software context for another. This is needed because there is only one guest TLB, and none of the entries are tagged to indicate which guest context they belong to. In guest mode, when guest segmentation and translation are enabled, two levels of address translation are performed by the hardware without software intervention. The first level uses the guest segmentation controls and the guest TLB. This translates an address from a guest virtual address or a guest direct map address to a guest physical address or GPA. The second level of translation uses the root TLB using the GPA in place of the virtual address that would normally be used. This second translation results in a physical address. The cache attribute used is that supplied by the guest context. In this second level of translation, exceptions in address translation are handled by root. The main takeaway from this is that the hypervisor completely controls the memory access to the L1 and L2 caches and physical memory by the guest. In addition, the hypervisor divides the memory up between guests, but makes it look like the guest OS has control of all physical memory. Here are the counterparts of the TLB instructions that operate on the guest TLB from root mode. These can be used by the hypervisor to initialize the guest TLB, monitor what is in the guest TLB, or to save and restore TLB entries on a guest context switch if necessary. All instructions that change an entry will only affect the TLB entries where the guest ID of the entry is equal to the CP0 guest control 1 RID. These standard TLB instructions have been modified to use the guest ID if the guest control 0 RAD field is clear. These instructions are used by the guest OS or the hypervisor to manage their respective TLBs. Now I'll cover exceptions. Exceptions in the virtualization module are broken down to those taken in guest mode by the guest OS and those that are taken in the root mode by the hypervisor. Of course, all exceptions while the hypervisor is running are taken in root mode by the hypervisor. In guest mode, the virtualization module is designed so that the guest OS can handle all exceptions that it is permitted to be as efficient as possible and not cause a mode switch. There are rules to determine which mode an exception is handled in. First is regarding the CP0 state exceptions. The exception is always taken in the mode whose CP0 state triggered the exception. For example, say the guest OS is Linux, and one of the processes in Linux issues an FPU instruction. The virtualization module first checks to see if the guest config1 FP field is set to indicate that there is an FPU, and then it checks to see the guest status CU1 bit is set to see if the FPU is enabled. If either of these is not set, then a guest exception will be raised and the Linux OS will handle the exception. If they are both set, then the root CP0 context is checked. There is a chance that the root status CU1 bit might not be set. Then the exception will be raised in the root mode and the exception will be handled by the hypervisor exception handler. For this FPU example, this is a way to control FPU sharing between the hypervisor and multiple guests. The hypervisor needs only to save and restore the FPU registers if an FPU instruction is actually used. In this case, the root exception handler will save the current FPU registers to the guest context that last used them and then restore the FPU registers for the current guest. While running in guest mode, and there is an exception caused by the root context, a mode switch is done to root mode and then the exception state is saved to the root CP0 registers. The hypervisor exception routine is expected to save whatever context it deems necessary so the context can be restored after the exception is processed. The reset, NMI, memory error, and cache error exceptions are always handled in root mode no matter what mode is executing. A hypervisor exception is caused by the guest executing an instruction where the instruction is either not permitted in guest mode or is not enabled in guest mode. I'll cover these guest privilege sensitive instructions in the next slide. The virtualization module can be configured to give control to the hypervisor when the guest OS tries to execute a privilege instruction. The guest privilege sensitive instruction can be triggered by a guest that is accessing a sensitive CP0 register or the execution of a privileged instruction. Any access to a CP0 register will cause this exception if the guest control 0 CP0 bit is not set. This table shows the guest CP0 sensitive instructions even if the guest control 0 CP0 bit is set. Access to any of the config registers will cause an exception if the config register bit CF is not set in the guest control 0 register. Access to the compare registers will cause an exception if the timer register access GT bit is not set in the guest control 0 register. Access to the page grain, wired, or any segmentation control registers will cause an exception if the address translation field AT is not set in the guest control 0 register. Access to any TLB related registers if the MMU guest bit GM is set in the guest control EX register. Access to any bad address register if the bad GB bit is set in the guest control EX register, and access to the user local, WRENA, user trace data 1, user trace data 2, K-scratch 1 through 6 if the OG bit is set in the guest control EX register. Accesses to the registers that control the shadow register sets, processor identification, common device memory map, cache, error exceptions, and debug exceptions save registers will always cause a guest privilege sensitive instruction exception to the hypervisor. A wait instruction will always cause an exception to give the hypervisor control over the power state of the core. Cache instructions will generally cause an exception so that no guest can read or write another guest's or hypervisor's cached instructions or data. The cache instruction guest mode enable guest control 0 CG bit allows the guest to execute instructions which use an effective address. An effective address is also known as a program address, which can be a virtual address that is mapped by the TLB or a direct map address from KSEG 0 or KSEG 1. If the cache instruction guest mode index enable is set along with the guest control CG bit, then the guest can issue index invalidate instructions. Index invalidate instructions will just invalidate a cache line, so it will do no harm to another guest or the hypervisor, but could cause some performance degradation. If the address translation AT field is not set so that the MMU is under guest control, then any TLB instruction will cause an exception. If there are no additional shadow register sets or access to CP0 registers are not allowed, the read GPR from previous shadow set or write GPR from previous shadow set instructions will cause the exception. If the guest access to coprocessor 0, guest control 0 CP0 bit is not set, then any guest execution of a privileged instruction will cause an exception. Note, if this bit is 0, then it overrides any other setting and will always cause a guest privilege sensitive instruction exception for any guest execution of a privilege sensitive instruction. Privilege sensitive instructions are defined in the Volume 2 of the Architecture Manual. Instructions that are supported depend on architecture release and the implementation which it is compliant with. The virtualization module can be set so the hypervisor can intercept all exceptions. This is done by setting the mode change bit guest control 0 MC and clearing the field change disable bit guest control EXT FCD. This is called a guest hardware field change exception. The guest hardware field change exception is triggered by a hardware change to one of two status fields. EXL that indicates an exception has happened, and TS indicates that the TLB is about to shut down due to a duplicate entry being placed into it. When an exception occurs, the guest context is updated with any information that is normally updated in accordance with the exception type, and EXL is set. The root context is modified by setting exception level bit root status EXL, setting the exception code field root cause EXC code to guest exit, and the root guest control GEXC code to indicate that the guest hardware field change exception occurred. Next, a mode switch will be done so the hypervisor can do what it needs to do in accordance with the system security policy. Once the hypervisor is finished and does an ERET, the mode switches and the guest begins processing the exception. Once the guest is finished and it does an ERET, then the mode switches again to root execution before returning to the normal guest execution. Once the hypervisor does an ERET, the mode switches back to the guest. If the reserve instruction bit guest control 0 RI bit is set, a guest-generated reserve instruction exception will be taken in root mode with no context change to the guest. For example, the execution of a DSP instruction in guest mode when the config3 DSP bits are not set, indicating that the DSP ASC is not implemented, will cause a reserve instruction exception. The guest OS can exit to the hypervisor with the instruction hypercall. The instruction takes a 10-bit immediate value, which is placed in the CP0 root bad instruction register.